Welcome to Unit 5, where we'll explore memory and input-output systems. I'm A. Sindhu Devi from the Computer Science and Business Systems Department at Jerusalem College of Engineering. Together, we'll dive into how computers store data and communicate with the outside world, key concepts for understanding how modern systems work. Let's get started. Let's start with memory, the part of a computer that stores data, instructions, and results the CPU needs to work. Memory isn't just one thing, it's organized in a hierarchy. That's because no single type of memory can be super fast, super big, and super cheap all at once. So, the system balances these trade-offs by stacking different kinds of memory, each with its own strengths. This hierarchy is key to how computers manage information efficiently. Let's talk about the memory hierarchy, a way computers organize storage like a pyramid. At the top, we have the fastest memories. They're small, costly, and volatile, sitting close to the CPU for quick access. As we move down, memories get slower, cheaper, and larger in capacity. These are non-volatile, meaning they keep data even when the power's off. This structure balances speed, cost, and size to keep everything running smoothly. Let's talk about memory hierarchy, the way computers organize different types of memory to work efficiently. At the top, we have the fastest, smallest memory, like registers and cache. Then comes main memory, which is larger but slower. Finally, there's storage, huge but much slower. This structure helps balance speed and capacity, so the system runs smoothly without breaking the bank on expensive, super-fast memory everywhere. Understanding this hierarchy is key to grasping how computers manage data. As we move down the hierarchy, things start to change in a few key ways. Speed goes down, it gets slower. Access time, or how long it takes to get to the data, goes up. But capacity grows, we can store more. And the cost per bit drops, making it cheaper to hold that data. This balance between speed, size, and cost is what shapes the entire memory hierarchy. Understanding this helps us design systems that are both fast and efficient. Let's take a closer look at how memory works in a typical computer system. Memory is organized in levels from the fastest and smallest to the slowest and largest. At the top, we have registers, incredibly fast but tiny in size and very costly per bit. Next is cache, still fast but a bit larger and less expensive. Then comes RAM, which balances speed and capacity. After that, storage like SSDs or hard drives, slower but much bigger and cheaper. Finally, backup or tertiary storage, the slowest, largest, and most affordable option. This hierarchy helps computers manage data efficiently. Registers are the fastest storage spots in a computer, right inside the CPU itself. They hold critical information we need instantly. For example, the program counter keeps track of the next instruction to run. The instruction register holds the current instruction. The memory address register points to specific memory locations. The memory data register carries data moving to or from memory. Then there's the accumulator, which stores intermediate math results. And finally, general-purpose registers handle temporary data. These registers keep everything running smoothly and quickly. Let's consider a simple instruction. Add R1, R2. Here, the CPU adds the values stored in registers R1 and R2. The key point is that the CPU can access these registers directly, no need to fetch data from slower memory like RAM. That direct access makes registers incredibly fast, speeding up processing significantly. This example shows why registers are essential for efficient computing. They keep data close and ready for immediate use. Cache is a small, super-fast memory that sits right next to, or even inside, the CPU. Its job is simple but crucial, to cut down the time it takes to grab data and instructions we use all the time. By keeping these close at hand, the CPU doesn't have to wait around. Modern processors usually come equipped with several layers of this cache memory, making everything feel quicker and smoother. Let's break down the different levels of cache in a CPU. First, there's the L1 cache. It's the smallest and fastest, sitting right next to each core for lightning-quick access. Next up is the L2 cache. It's bigger than L1 but a bit slower, usually dedicated to a single core or a small group. Finally, the L3 cache is the largest and slowest of the three, often shared across multiple cores. Together, these caches balance speed and size to keep data close and processing smooth. RAM, or random access memory, is where the computer keeps programs and data it's using right now. Think of it as the workspace for your CPU, everything it needs quick access to. This includes the operating system running behind the scenes, the applications you're using, variables and objects your programs create, instructions the CPU follows, and temporary data that changes as you work. RAM is the main memory that keeps everything ready and fast. Without it, your computer would slow to crawl. Let's talk about two key types of memory, DRAM and SRAM. DRAM is what we usually use for main memory. It offers high capacity at a lower cost, making it ideal for system RAM. On the other hand, SRAM is faster than DRAM and is typically used for cache memory, where speed really matters. Both have their roles, balancing cost, speed, and capacity to keep our systems running smoothly. Secondary storage is where we keep our data safe for the long haul. Unlike RAM, which loses everything when the power goes off, secondary storage holds onto information even without power. Think of SSDs, hard drives, USB sticks, and memory cards, all examples of this kind of storage. This persistence is what we call non-volatile storage. It's the backbone for saving files, applications, and everything we want to keep around, no matter what happens to the power. Let's talk about volatile memory, a type of memory that loses its data as soon as power goes away. Think of it like a whiteboard that erases itself when the lights go out. Common examples include registers, cache, and RAM. These are super fast, but they need constant power to hold onto information. This contrasts with non-volatile memory, which keeps data even when the device is off. Understanding this difference is key when we design systems that balance speed and persistence. Let's talk about non-volatile memory, a type of storage that holds onto data even when the power's off. This means your information stays safe, no matter what. Common examples include SSDs and HDDs, which store everything from your documents to your apps. Then there's ROM, which holds essential instructions for your device. And flash memory, found in USB drives and memory cards, is another popular form. All of these help keep your data intact without needing constant power. Let's talk about non-volatile memory, a type of storage that holds onto data even when the power's off. This means your information stays safe, no matter what. Common examples include SSDs and HDDs, which store everything from your documents to your apps. Then there's ROM, which contains essential system instructions. And flash memory, found in USB drives and memory cards, letting us easily move data around. Non-volatile memory is the backbone of how we keep information persistent in the digital world. Let's imagine the CPU could only use RAM. The CPU is incredibly fast, but RAM is slower by comparison. To bridge this gap, we use a hierarchy: CPU, then cache, then RAM, and finally SSD. This setup creates the illusion that the CPU has access to a large pool of very fast memory. By keeping frequently used data closer to the CPU, we speed things up and keep everything running smoothly. That's why memory hierarchy is so important. Memory hierarchy is effective because programs tend to access data in predictable ways. This behavior is known as locality of reference. There are two key types we need to understand. Together, these principles explain why certain data stays close to the processor, making memory access faster and more efficient. Let's dive into the principle of locality and see how it shapes the way memory systems are designed. When a program uses certain data, chances are it'll use that same data again pretty soon. This idea is called temporal locality. Take this example, a loop adding numbers from 0 to 999. The variable sum gets accessed over and over inside that loop. Because of this repeated access, it makes sense to keep sum as close to the CPU as possible. That way, the program runs faster and more efficiently. Temporal locality helps us understand why. When a program reads from one memory address, it usually needs data from nearby addresses too. For example, if it accesses an array element at address 1000, it's very likely to access the next elements at 1004, 1008, and so on. This pattern is called spatial locality. Caches are designed to take advantage of this by loading not just the requested data, but also the data close to it, improving performance and efficiency. It's a simple idea, but a powerful one. Let's talk about cache misses and hits. A cache miss happens when the data the CPU needs isn't in the cache. The CPU checks the cache, comes up empty, then has to go all the way to RAM to get it. That takes more time. On the other hand, a cache hit means the data is right there in the cache, ready to go. That's much faster. Understanding this difference is key to grasping why cache performance matters so much. When we talk about memory, one thing stands out: each level has its own speed. How fast you can access data depends on the processor, the type of memory, and the overall system design. The main idea to remember is this: the closer the memory is to the CPU, the faster it is. But there's a trade-off. That speed comes with smaller size and higher cost. So speed, size, and price all balance out in the memory hierarchy. Here, we have a diagram that brings the concepts we've discussed into a clear visual form. It helps us see how the pieces connect and interact, making the abstract more concrete. Take a moment to follow the flow, notice the relationships, and let the structure guide your understanding. This visual will be a useful reference as we move forward. Let's break down some key concepts in memory, starting with memory bandwidth. That's how much data can move in a given time, usually measured in gigabytes per second. Then there's latency, which is the delay before any data transfer actually starts. Cost per bit tells us how much it costs to store a single bit of data. Capacity is the total amount of data memory can hold, from kilobytes to terabytes. And finally, access time, the time it takes to read or write data. These ideas shape how memory performs and scales. Cache memory acts like a fast lane between the CPU and the main memory. It holds the instructions and data we use most often, so the CPU doesn't have to wait around. Two key ideas help this work smoothly. First, cache mapping techniques decide where a block from RAM should go in the cache. Second, cache replacement techniques figure out which block to remove when the cache is full. Together, these keep the system running efficiently. Now, let's focus on the relationship between cache and organization. How we arrange data in the cache can make all the difference in speed and efficiency. Cache organization determines how quickly the processor can find what it needs. It's about structure, the way data is stored, accessed, and managed. Getting this right means smoother performance and smarter use of resources. This is a key piece of the puzzle as we dive deeper into system design. RAM is organized into fixed-size blocks, while cache is split into fixed-size cache lines. This setup is crucial because the way we map memory blocks to cache lines determines how efficiently data moves between RAM and cache. Essentially, the mapping technique decides which memory block can be stored in which cache line, shaping the speed and performance of our system's memory access. This slide sets the stage for understanding those mapping methods in detail. When it comes to cache memory, there are three major techniques for mapping data. First, direct mapping, a straightforward approach where each block of main memory maps to exactly one cache line. Next, fully associative mapping, the most flexible method, letting any block go anywhere in the cache. Finally, set associative mapping, a hybrid that balances speed and flexibility by grouping cache lines into sets. Understanding these techniques helps us grasp how caches keep data close and access fast. In direct mapping, every block of main memory has just one specific spot in the cache where it can go. There's no choice, no flexibility, just a single line reserved for that block. This is determined by a simple formula that links memory blocks to cache lines. It's a straightforward approach, making cache management faster, but it also means some blocks might compete for the same spot, causing potential conflicts. Here, we see a simple example of how memory blocks map onto cache lines. Imagine main memory has 16 blocks, but our cache only holds 4 lines. Each block in memory corresponds to a cache line based on a repeating pattern. So block 0 maps to line 0, block 1 to line 1, and so on. When we reach block 4, it wraps back to line 0. This cycle continues, showing how limited cache space forces blocks to share lines, which is key to understanding cache behavior. One downside here is that conflict misses can happen a lot. Imagine the CPU keeps jumping between blocks B0 and B4. Each time it does, one block kicks out the other, causing repeated replacements. This happens because only one block can sit in the same cache line at once. On the plus side, this setup is simple, inexpensive, and offers fast lookups. Plus, it's easy to build in hardware. So there's a real trade-off between simplicity and potential conflicts. With fully associative mapping, a memory block isn't tied down to a specific spot. Instead, it can go anywhere in the cache. This flexibility means the system can place data wherever there's space, which helps reduce conflicts. But it also means the cache has to check every line to find what it's looking for, making the search more complex. So, fully associative mapping offers freedom in placement, but at the cost of more complicated lookup. When there's no fixed cache line for a memory block, the system gains a lot of flexibility. This design cuts down on conflict misses, which can really slow things down. But there's a trade-off. The cache has to check the requested tag against many, sometimes all, entries at once. That means the hardware gets more expensive, with extra comparison logic and added complexity. It's a balance between performance and cost, and understanding this helps us see why cache design choices matter so much. Set associative mapping gives us the best of both worlds. It blends the simplicity of direct mapping with the flexibility of fully associative mapping. Here, the cache is split into groups called sets. Each set holds several cache lines, which we call ways. For instance, in a two-way set associative cache, each set contains two ways. This structure helps balance speed and efficiency when accessing data. Let's talk about how a memory block fits into a cache. Each block belongs to one specific set, but it can be placed in any line within that set. This flexibility helps the cache manage data efficiently. The formula on screen shows how we determine which set a block maps to, guiding where it can be stored. Understanding this mapping is key to grasping how caches optimize memory access. Let's break down this example of a cache with 8 lines, organized as a two-way set associative cache. That means each set holds 2 lines. To find the number of sets, we divide the total lines by the ways, so 8 divided by 2 gives us 4 sets. The table here shows how blocks map to sets, cycling through sets 0 to 3 as the blocks increase. This mapping is key to understanding how data is stored and accessed efficiently in the cache. Now we're moving into block 4. This section builds on everything we've covered so far, diving deeper into the core ideas. It's where the concepts start to connect in more meaningful ways, setting us up for the final stretch. Let's keep our focus here. The insights in this block are key to understanding the bigger picture. Let's break down the 3 main ways caches map data: direct, fully associative, and set associative. Direct mapping puts data in one specific line. It's simple, cheap, and fast, but conflict misses are high and flexibility is low. Fully associative lets data go anywhere, offering very high flexibility and almost no conflict misses, but it's complex and costly. Set associative strikes a balance. Data can go anywhere within a set, making it moderately complex and cost-effective, with fewer misses. This is why modern CPUs favor it. When we look at a CPU address, it's usually split into 3 parts: tag, index, and offset. The tag tells us which memory block is currently stored in the cache. The index points to the specific cache line or set where that block might be. And the offset zeroes in on the exact byte or word inside that block. How these parts work together depends on the mapping technique the system uses. This breakdown is key to understanding how cache addresses are formatted. Let's talk about direct mapping. It's a straightforward way to connect memory addresses to cache locations. Here, the line or index in the address points directly to a specific spot in the cache. There's no searching around. The address itself tells the cache exactly where to find the data. This makes access simple and fast, but it also means each cache line has only one possible place to go. It's a trade-off between speed and flexibility. Here, we're looking at a fully associative address system. Unlike other methods, there's no fixed index because a block can be placed anywhere in the cache. Instead, the tag of the incoming block is compared with the tags of all cache entries. This gives us flexibility, but it also means every tag must be checked, which can impact speed and complexity. It's a trade-off between freedom of placement and search effort. Here, we're looking at how the set helps narrow down where to search. First, the set tells us which group of locations to focus on. Then, within that group, the tag is compared against the stored entries to find a match. This method, called set associative addressing, balances speed and flexibility by limiting the search to a smaller, manageable subset rather than the entire memory. It's a smart way to keep things efficient. Replacement matters most when several blocks want the same spot in the cache. This challenge shows up clearly in fully associative caches, where any block can go anywhere, and in set associative caches, where blocks compete within specific sets. Managing which block stays and which gets replaced is key. That's where cache replacement techniques come into play. They decide how to keep the cache efficient, balancing speed and hit rates as blocks come and go. When it comes to managing limited resources, like memory in a computer, we often need to decide which items to replace. There are a few common strategies for this. First, LRU, least recently used, which removes the item that hasn't been accessed for the longest time. Then FIFO, first in, first out, which simply replaces the oldest item. Random replacement picks an item at random, no questions asked. And finally, LFU, least frequently used, which targets the item accessed the least over time. Each has its own strengths and trade-offs. Let's talk about LRU, which stands for least recently used. It's a method that helps decide which block to remove when we need space. The idea is simple. We remove the block that hasn't been used for the longest time. For example, if we need to load a new block, say block E, and block B was the least recently used, then B gets removed. E takes its place. It's a smart way to keep the most relevant data handy. One big advantage here is performance. Programs often reuse the same data or instructions over short periods, which we call temporal locality. This means caching or tracking usage can speed things up significantly. But there's a downside: to keep track of what's being used and when we need extra hardware. That adds complexity and cost. So while the performance boost is real, it comes with a trade-off in system design. Let's talk about FIFO, first in, first out. It's a straightforward way to manage cache. When a new block like E arrives, the oldest block A gets removed to make space. The new block then takes its place. The big advantage here is simplicity. It's easy to understand and implement. But there's a downside: the oldest block might still be in use, so removing it could hurt performance. FIFO's strength is its simplicity, but that can also be its weakness. Let's talk about a cache replacement method that's as straightforward as it gets: random replacement. Here, when the cache is full, we simply remove a randomly chosen entry. The big advantage: it's incredibly simple, which means it requires very little hardware overhead. But there's a catch. This method doesn't consider how often or recently a cache entry has been used. So the decision to replace is blind to usage patterns, which can sometimes hurt performance. Still, its simplicity makes it appealing in certain situations. Let's talk about LFU, or least frequently used. This method removes the block that's been accessed the fewest times. Imagine a new block, E, arrives. We need to make space, so we look at the access counts. Block B has only been used twice, the lowest frequency. So B gets removed. It's a simple way to keep the most popular data handy and clear out what's barely used. This slide highlights a crucial difference we need to understand. When we talk about mapping, we're asking, where can a memory block be placed? It's about finding the right location. Replacement, on the other hand, deals with what happens when there's no space left. Which existing block should we remove to make room? So mapping is about placement, replacement is about eviction. Both are key to managing memory efficiently. Let's look at an example to bring these ideas to life. Examples help us see how concepts work in the real world. They turn abstract ideas into something concrete. They show us the impact, the challenges, and the possibilities. So, as we move forward, keep this example in mind. It's a lens through which we can better understand the bigger picture. Let's look at a simple example with a two-way set associative cache that has 4 sets. Imagine blocks arriving in this order: 0, 4, 8, and 12. To figure out which set each block goes to, we use the formula. Set equals block number modulo 4. This means we divide the block number by 4 and take the remainder. It's a straightforward way to map blocks to sets, and it helps us understand how the cache organizes data. Here, we're looking at a simple pattern, numbers divided by 4. 0, 4, 8, and 12 all leave no remainder when divided by 4. That means they all belong to what we call set 0. But there's a catch: set 0 only has 2 ways to assign these blocks. So even though 4 blocks want the same set, the set itself can't hold them all at once. This sets the stage for a deeper look at how we manage conflicts in allocation. As block 8 arrives, we have to make room by removing one block. Using the least recently used method, block 0 is the oldest, so it gets removed. Then, block 8 is inserted. This keeps the cache updated by always replacing the block that hasn't been used for the longest time.
Thank you for watching. Please do like, share and subscribe my channel for more videos.